This video is to explain our calcium analysis lab in water. We've been talking about solubility of different things in each other, like likes, dissolves, and likes. And we've also looked at the effect of temperature and the ability of something to dissolve in water. So our lab relates to the ability of calcium to dissolve in water. And the largest source of calcium in our water is going to come from calcium carbonate. Now, we live in a region where there's a lot more calcium in water, and a lot of us do have water softeners to account for that. So how does it get in there? Well, here's a diagram of typical underground water. Rain, of course, hits the surface of the earth, and that rain, filters down through soil and rocks, sand, gravel. And what happens is, as the water passes through all of this, some of the calcium carbonate dissolves, into water, and this reaction here makes calcium positive too, and we're going to call those aqueous ions, plus a carbonate minus 2 aqueous. And it starts off as solid. But calcium does not really have that great a solubility, especially in the form of calcium carbonate. So trace amounts of calcium dissolve in. And of course, there's other natural calcium in soils and things like that. But its solubility is quite low. So our concentration for calcium in water comes out as parts per million. It's also known as milligrams, per liter. And we'll talk more about concentration units pretty soon. So because of such a small quantity, we want to use an indicator to help us see it. So our lab setup was pretty simple. We have a water sample in a beaker or a flask, and we have a compound known as EDTA. That's an abbreviation for a more complicated name, ethylene diamine tetraacetate. And the calcium is in our water, and we're going to put in an indicator called Calcoon in order for us to see how much calcium is in the water. Let's see how this actually happens. We are going to look at this part right here and kind of blow it up the size. This is just our water sample here. So what does the water sample look like if we were to make it really, really large? Well, there'll be freely floating calcium ions in the water mixed all around, and we can't really see that. And how much is there? Again, not much. We're talking parts per million. Here, of course, is the surface of our water, and this is where our calcium is floating around, completely dissolved in the water. But our water looks totally clear because we can't see those. Calcoon. This is our indicator. And this is the sodium form of it. When we drop calcoon in the water with the calcium in it, we're going to displace the sodium and replace it with a calcium. So what's going to happen, the calcoon indicator is going to latch on to the calcium. Now, what color does that make? Well, when calcium is on the calcoon indicator, it's going to be a brandywine color, like a reddish pink color. When calcoon does not have the calcium on it, it's actually a blue color. So it's the fact that when we have calcium on there, there's a certain color, and when it doesn't have calcium on it, is a different color. We can tell how much calcium is in the water, because of that color change when we're done. We're actually looking for purple, to be our endpoint. Now, why purple? Well, a red color and a blue color, makes purple. It's not a real true purple because we're starting with that brandywine color. So how does this work then? Well, let's go back to our calcium sample. When we drop the calcoon in there, what we do is we make complexes of calcium and calcoon. So I'm going to show that right here. I'm doing little dash lines here, and I'm writing the calcoon in here right now. So what happens is the calcoon indicator binds with all the calcium present, in the water. So I'll do one more right here, put a calcon right here. Okay, and that makes a brandywine color. Why? Because all the calcon is now complex, is what we call it, okay, with the calcium that's in the water. Okay, that's the start of the experiment. So this is what our beaker should look like initially, or our flask should look like, a nice brandywine color. Now what's EDTA all about? Let's look at its structure. Well, EDTA has these oxygens here, and notice there's 4 of them, okay? That calcium, okay, will also complex too. So, and that's a very, very, very strong bond there. So this is our molecule structure. So when we drop EDTA into solution, what happens is the Calcoon indicator has to release the calcium. Why? Because EDTA kind of steals it away from it. Okay, so let's go back up to our slide here. Okay, so here's our Calcoon indicator. Now what happens is, and EDTA comes in and essentially steals away, okay, the calcon. Okay, and I'll show one of these here, and you get the idea of what actually happens here. So now the calcon is off by itself. And this, of course, is a blue color when calcon's all by itself. So what happens is as you continue to add EDTA, all of the calcons are kicked off the calcium, and EDTA takes the place of all of them. Okay, now remember that makes a blue color. So why are we interested in purple? Okay, well, purple is the very end point, okay, when all of the calcon is just about kicked off the calcium. So when we get the purple color, I'll write the purple down here again, that tells us to stop adding EDTA, because we're just at the moment where all the calcons have been released from the calcium. So that's kind of what we want. We want that moment. Now, actually, if you get purple, adding one more drop of EDTA will cause it to go to the blue. Okay, so it's very sensitive at that point. So our end goal is to try to get the purple, okay, to tell us, you know, how much we actually have for the calcium in the water. Now what we do, okay, in our Barré tube, if I can go back to that slide really quickly here, all the way back up here to our Barré tube, there would be a beginning volume of EDTA in here. I'll just draw a line. And then we let the EDTA slide into or drop into the water. And then there's going to be a final volume. So let's call this volume 1, and let's call this one volume 2. Okay, we really want the change in, so I'm going to say delta. Delta means change in volume. Okay, that's going to, of course, be volume 2 minus volume 1. Again, the more EDTA you add, okay, to the water, the more calcium, okay, that is in the water. And we can use the known concentration of the EDTA, okay, to figure out what our parts per million calcium is. For this lab, the way I've mixed it up, okay, for what you do is you multiply your change in volume by 20, and that'll get you your parts per million of calcium in the water. And that's how our lab works. Okay, we will go to our lab now and finish up our calculations and anything else we need to do.